In this video, I want to talk about the definition and meaning of average velocity. This will reveal some rather deep insights about mathematics and physics. Let's start with a position versus time graph that represents the motion of some object. You've already seen that the average velocity of the object between 2 points in the motion is defined as the change in position divided by the time interval over which that change occurs. The average velocity is the slope of the straight line connecting those 2 points. Let me start out with a question. How is this definition of average velocity in any way an average? I understand an average is calculated by taking a set of data points, adding them together, and dividing by the number of data points in the set. Is this second idea of an average velocity in any way connected to the definition of average velocity just discussed? This is the question I want to explore in this video. Let's start with an experiment. Consider an object that starts from rest and speeds up at a constant rate of 2 meters per second every second. We will find the average velocity of the object between 2 seconds and 3 seconds using two different methods. First, we will find the average velocity of the object between 2 seconds and 3 seconds from its velocity versus time graph. Its velocity at 2 seconds is 4 meters per second. Its velocity at 3 seconds is 6 meters per second. The average velocity in this interval is the sum of these two velocities divided by 2, giving an average velocity of 5 meters per second. Hopefully, it feels fairly intuitive that the average velocity is the midpoint between 2 seconds and 3 seconds. On the other hand, let's try to find the average velocity of the object from its position versus time graph. Here we see that the position of the object at 2 seconds is 4 meters and the position at 3 seconds is 9 meters. Drawing a straight line through these 2 points, the average velocity of the object is the slope of this line, which is the change in position over the change in time, which is 5 meters per second. The same result as we found from the velocity versus time graph. It turns out that for the case of motion with constant acceleration, these two ways of finding average velocity will always give consistent answers. Showing this will take a little bit of math. Consider constant acceleration motion described by x of t equals x0 plus v0t plus 1/2 at squared. We will pick two randomly chosen points on this graph as shown. Below it is the corresponding graph of velocity versus time for the same motion. Let's identify the same 2 points in time and their corresponding velocity components. If we take the definition of average velocity as a change in position over a change in time and substitute the position equation into this, we get the following expression. Rearranging the terms a little, you see that the two x0's cancel out. Use the difference of squares formula to factor the squared times associated with the acceleration. Now, a factor of t2 minus t1 can be cancelled out of the equation, leaving us with 1/2 a into t2 plus t1 plus v0. Splitting v0 into halves and grouping these two halves with each with 1/2 a t1 and 1/2 a t2 respectively, you might recognize that the first group of terms represents the velocity of the object at time t1, and the second group represents the velocity of the object at time t2, which shows that the average velocity of the car is the sum of the two velocities divided by 2. To summarize, these two different approaches to finding average velocity are mathematically equivalent, at least for the special case of constant acceleration. Let's consider a more general example, this time of a pullback car that speeds up for 4 seconds and then slows down and comes to a stop at 8 seconds. And let's ask the question, what was the average velocity of the car over the entire trip from 0 seconds to 8 seconds? Clearly, taking the velocity at 0 seconds and the velocity at 8 seconds, adding them together and dividing by 2 will give us 0, which is not going to be the right answer. But let's take our intuition for what an average velocity is and apply it here. What if we identify 8 velocities at equally spaced points in time on the graph, add those 8 values together and divide by 8? We get an estimate of the average velocity of the car over the 8-second interval. How might we improve our estimate for the average velocity? Well, Let's sample 16 points in the graph equally spaced in time. Repeat this for 32 points, then 64 points, 128 points, and 256 points. You notice that it appears that our approximation of the average velocity is converging on a fixed value. What if instead we plot the position versus time graph for the pullback car? Identify the position at 8 seconds, subtract from this the position at 0 seconds, and divide by 8-second time interval to find a straight line slope between the 2 points marked on the graph. Remarkably, the average velocity comes out to be exactly the same value as we just calculated by sampling many points on the velocity versus time graph. This is not an accident. What I want to show you is that these two methods of calculating average velocity are connected by the fundamental theorem of calculus. Returning to the velocity versus time graph, the number of points n that we sample over the graph is the full time interval delta t divided by the small time step dt. Thus, 1 over n is dt over delta t. When we calculate the average, we replace 1 over n with dt over delta t and rearrange the equation slightly. Now imagine we sample infinitely many points. The sum turns into an integral from 0 seconds to 8 seconds of v of t dt. This integral is still divided by delta t. But the fundamental theorem tells us that this definite integral is the antiderivative of velocity, or position, at 8 seconds minus the position at 0 seconds. Since this is divided by the time interval of 8 seconds, this proves that the first method of finding the average is equivalent to the second method, by finding the slope of the straight line graph that connects the starting and ending points of the motion we are considering. There are two key takeaways from this video. The first is that the average velocity from the position versus time graph by taking delta x divided by delta t is indeed an average velocity in the intuitive sense that we understand an average as a sum of data points divided by n. To prove this, we had to use the fundamental theorem of calculus, which says that the answer to an integral is found by subtracting the value of the antiderivative of the integrand at the endpoints of the interval we are considering, and it doesn't matter what goes on in the middle of the graph. This is remarkable in itself, but the second lesson I'd like you to take away is that you have learned how to take a time average of a function. The time average is the integral of the function with respect to time divided by the time interval over which you are integrating. This is useful in all sorts of physics topics that you will encounter in the future, from electricity and magnetism to quantum mechanics.